Today on Applied Science, I'd like to talk about my adventures in making Gecko tape. If you haven't heard, Gecko tape is sort of an alternative to the currently available adhesive tapes. It actually works by a different mechanism, and it's not really a commercial product yet, but it's gotten a lot of press in sort of popular science articles. And so it has a few attractive qualities that make it better suited than these commercial adhesive tapes. So first, let's talk about how these actually work. Each one of these tapes has a layer of adhesive on it. There's actually a chemical on here, and the reason it's sticky is because it makes a chemical bond with whatever you're sticking it to. And so the problem with this is if you get it wet or if it gets dirty, the chemical becomes coated with water or the dirt, and then the tape is no longer sticky. So if you're constantly taking the tape off and replacing it, eventually the adhesive will wear out and the tape is no good anymore. The difference with Gecko tape is that this works by a mechanical method. It's actually using a different sort of molecular bonding. And so in this video, I'm going to talk about all the things I've tried so far. Unfortunately, it's not working just yet, but with your help, hopefully it will. Like the name implies, Gecko tape is actually modeled after the foot of a gecko. And so part of the reason that the gecko's foot wouldn't work with a conventional adhesive like this is because it would quickly become loaded with dirt, and the gecko wouldn't be able to stick and walk upside down, which is critical to its survival. So the Gecko tape is sort of our answer, or at least our modeling of this sort of natural phenomenon. And the trick is that the gecko's foot has a whole bunch of hairs on it, and the hairs get into very intimate contact with the with the surface that the foot is stepping on. And it's these small intermolecular bonding forces that produce an attractive force between the hair ends and the surface that it needs to stick to. So most surfaces aren't perfectly flat. They're not atomically flat. So if you want to get something into very close contact with it, it needs to be very conformable. And even something soft like this silicone rubber, it's really not, you'd think, well, if the silicone rubber has a flat surface here and we put it down on something flat, it's in contact, but not really. At the microscopic level, there's always going to be, hills and valleys, and it's not going to make really great contact. So nature's solution to this problem was to have a structure that has very small hairs, and when you push that down onto a surface, sort of the end of each hair will make really good contact with the surface. And then, if you have millions of these little hairs, it's basically almost as good as having a solid flat piece into, perfect atomic contact. So whereas the commercial adhesive tapes use perhaps hydrogen bonding or something like that, where you have this chemical adhesive layer that's going between the tape and the surface, the Gecko tape works by van der Waals forces, which are present between all molecules as far as I know. But the trick is that you have to get the two surfaces really, really close together, like less than, 1 nanometer, a few nanometers or something. It basically has to be in contact. And as I mentioned, even if you cast a perfectly flat piece of tape and you put it onto a perfectly flat object like this, it's not even close to good enough contact. You really need this conformable architecture. So the Gecko has adapted sort of a two-layer system where it has pillars coming off of its foot, and then there's even hairs that are a finer structure even coming off of that. And so between the pillars and the hairs, it can really conform and have a huge amount of surface-to-surface contact. The actual material itself of the hairs and the thing that it's walking on is not particularly important. It's just the fact that it's in such close contact is what makes this whole system work. So anyway, I'm really interested in this, and I searched the internet for instructions on how to make Gecko tape, or at least what the techniques are being used in these research labs. And lo and behold, I actually found detailed, dedicated instructions for how to make your own Gecko tape at home. And it even had part numbers for all of the stuff that you'd need. And this is sort of the key ingredient here. So the idea is that you make the Gecko tape by casting the silicone rubber. And it's pretty easy. You just mix it up, kind of like 2-part epoxy, but the ratio is much greater than 1-to-1. And you pour this onto a mold, and hopefully the mold has holes in it, just like these we want to form pillars, and so the mold has to have holes in it. So we're going to pour the silicone onto that and then demold it, and then we'll have this forest of pillars coming off, and that's the structure we need to make this whole thing work. So it sounds reasonable, and the instructions are very clever. So they're going to use this interesting membrane here to make our silicone cast. And of course, I'll put links to all of this in the description, so definitely check that out. These are actually pretty cool. This deserves a little 1-minute side note all by itself. This is a track-etched membrane filter. And so the idea, as I mentioned, we want a whole bunch of little holes in here so that when we cast our silicone rubber, it goes down into the holes and we end up with this forest of pillars. So the way that you make this track-etched membrane is you start with a really thin sheet of polycarbonate, standard, you know, just like unbreakable safety glass or whatever, and you expose it to a radiation source. I believe it's probably a beta source, but I couldn't quite find out for sure. And the trick is the beta particles are going really fast, and they'll actually go all the way through the polycarbonate sheet because it's so thin. We're talking 10 or 20 micron or something like that. And then you put this into an etchant, and where the beta particles have gone through this really thin polycarbonate sheet, it's actually weakened the chemical structure of the plastic a little bit. And the etchant will attack only the weakened areas. So as the beta particles go screaming through these sheets, then you put this into the etchant bath, you'll end up with a hole etched in just the places where the particle has gone through. And the longer that you leave it in the etchant bath, the wider the holes will become because it sort of etches from the inside of the hole out. So it's a really easy way to get a very uniform hole size. So let's take a look at what one of these looks like under the scanning electron microscope. This is the millipore membrane that was mentioned in the instructions for making Gecko tape, and it has a 5 micron hole size, and it's pretty much identical on the top and the bottom. I also bought GE Wattman brand filters, and these have a 3 micron hole size, but I can tell they're built, or they're made with a different process because the one surface is very shiny and the other surface is very rough. So clearly the etchant that they used to make these filters was a little different. It actually attacked the polycarbonate a bit more. So you can kind of tell which side of the filter was exposed to the etchant. Anyway, so I thought that was pretty cool. What you do, according to the instructions, is you take one of these filters with the tiny holes in it and put it down onto some double stick tape, and then you pour the silicone, you mix up a batch of silicone. This is actually tin cure silicone, RTV silicone from Tap Plastics. And amazingly enough, the silicone will actually flow down into those 5 micron holes, all the way to the bottom even, so through the thickness of this membrane. And then when it cures and you peel this off, you end up with the structure we wanted to make this simulated gecko foot. And it all works the way it's supposed to, but the structure that it creates doesn't function as well as a gecko foot. In fact, it functions less well than a solid slab of silicone, as I'll show you. So just to give you a rough idea of how good the silicone is by itself, even though I spent a lot of time saying, well, if you put something in contact like this, even though the contact area, even though it's flat, is not very good because there'll be microscopic hills and valleys, it's actually pretty good. So just to give you sort of an idea of how sticky this thing is, I just sort of stuck it down like that, and with almost no pressure applied, I can pull this heavy piece of plastic around. So you can see that. Okay, so then this is the silicone that I made by casting the silicone in the membrane, just like it was said in the instructions. And if we put this on here, I know that it's kind of hard to see on the camera. You really need to get a tactile sense of this. No matter how much I baby this and no matter how careful I am, the friction coefficient with the so-called Gecko tape is way, way worse. In fact, this is almost sort of an anti-friction material. Like, this is really kind of, it's worse than just flat. I mean, it's basically worse than a lot of other things. So it doesn't work. And then I started searching around on the internet a bit more and found someone's thesis or dissertation where they actually mentioned these instructions and how it couldn't possibly work for a lot of reasons that we're going to get into. So, I wanted to see it first. So let's take a look with the scanning electron microscope again at what these pillars look like. Okay, you can see that, yeah, the casting process did work. And you can also see that the direction of the tracks that are etched through this plastic is not, they're not perpendicular to the surface. They're actually kind of all different directions. And that's because the radiation source doesn't just shoot out, beta particles in one direction. They're kind of going all different directions. So that's one problem. The other problem is that the pillars have a really high aspect ratio. They're kind of like wet noodles just, falling down over there because they're too long. And so I mentioned that the thickness of this membrane is like 10 or 20 micron or something like that. This is one of them right here. You can see that it's really, really thin. In fact, it's so thin that just the static attraction makes it really kind of difficult to handle. It's thin stuff, but it's still way too thick. So the relative thickness of this thing compared to the 5 micron, pillar diameter is so high that the pillar just folds over. And we don't really want it to fold over like that. What we want is the thing to be, fairly stiff, so that when we put this down onto the surface, the pillars kind of have enough rigidity so that the ends of the pillars touch the surface and make a good contact there. If they're all just flopping around, then the whole Gecko thing doesn't work. So I did a little bit more searching and found another group that instead of doing straight pillars like this, they were doing angled kind of wiper blades almost. Again, microscopic. We're talking, a couple microns thick or a couple microns long and maybe a pitch of 500 nanometer. And I thought, well, that's pretty cool. Maybe there's actually a structure that I can find kind of around in everyday life that sort of mirrors this, because they were using photolithography to make their parts, which I'll talk about a little later. And I came up with the idea of casting the silicone onto really, really fine metal files. So I did a little bit of research and found out that you can get these Swiss metal files that are quite a bit finer than the so-called American grades of files. So typically a smooth file is the smoothest thing you can get commonly, at least in this country or around here. If you go to your local hardware store in the US, a smooth file is considered the finest thing you can get. But if you go online to a specialty store, you can get this Swiss file, and I've never seen a file this fine. This thing is really, really fine. I think the pitch is around 20 or 30 thou of an inch. I'll put the exact numbers in the description. But anyway, I made a whole bunch of different castings with different files and different viscosities of silicone. You can kind of thin the silicone and make it into a stiffer or more flexible stuff. And as you might expect, the results aren't that great, but they are unidirectional, surprisingly. So I did find that with a specific file pitch, I kind of have to put a little bit of weight on the tape to make this work, but you can kind of see in one direction it works about that well, and then in the other direction it's not even close to as good. And the reason is that the teeth are asymmetric, and when the teeth are getting pulled sort of in their direction, they kind of fold down and create more contact with the surface that they're bonding to. If they're going the wrong way, when you pull them this way, they just sort of buckle and flap around and they don't create that great contact. So if you were interested in using Gecko tape as kind of a robotic foot or grabber or something, having a unidirectional adhesive surface is actually very nice, because you can make like a wall climber. Gravity is always trying to pull you down. So you can make the wall climber, you can make the foot basically work just the way you want. So if you put a lot of weight on it, you can get good stiction. And then to lift the foot, you actually push it upwards and it will instantly detach, because it's a one-directional gripper. So after this, I realized there's no way I could get a metal file that was fine enough to get close enough contact again. Another problem with the metal file is that the teeth are sharp on the top, but unfortunately we're making a casting and we actually want the teeth to be really sharp in the bottom, because when we do the casting and peel it off, it's actually the tips of the casting that are going to be interacting with our surface, and that's going to be formed by the bottom of the file. So basically just the manufacturing of this isn't really made for it. Even though it was a good idea, it's not really going to work out. So then I had another great idea. What about using a CD as the former? So that's pretty cool. So we're talking, this thing has a pitch between the pits and lands of, a few micron or something on that order. But I didn't know how deep they were. So I was able to make a silicone cast of a CD, and it is this one. So I came home one day after letting my silicone cast there and tried it out. And I was actually really excited. Hey, it works really well. In fact, way, way better than the files, way better than the official Gecko tape instructions. And then I of course tried it compared to the actual just flat cast on glass silicone, and it's not even quite as good as that. So so clearly there's still some more work to be done here. The biggest problem is that the aspect ratio of these magic pillars is not quite right. It needs to be about 4:1. So if the If the spacing between the pillars, or if the size of the pillars is on the order of 500 nanometer, that means the depth has to be 2 micron. And in the CD's case, if it's like a few micron in diameter, then we're going to be like maybe 4 to 8 micron deep or something like that. And so far, I haven't found any kind of easily accessible mold that has this correct aspect ratio and a high density of the pillars. The other problem with the track etched membrane is that these wet noodles are just spread out way too far. I mean, we want like dense packing to make this thing work. So all of the research groups that are doing this are pretty much using photolithography, which involves casting a photosensitive layer, and you can control the thickness of the layer by spinning it in a spin coater. And the faster you spin it, the more centrifugal force we get, and it makes the layer thinner, so that we can control the thickness that way. And then what you do is expose your micron scale pattern with ultraviolet light and etch it away. So we can basically make little holes of almost any width and depth that we want with this system. The problem is that I don't have any way to print micron scale stuff. So I've done photolithography before, but I've always used a laser printer's transparency. And there's no way to get down to microns with that. So I need like a lensing system, but then the lenses don't pass ultraviolet light, and there's a lot of problems involved. So I need your help to figure out how to pull this off. There's a few interesting ideas that I'm sure will come up in the comments, but basically we need to create this about 500 nanometer by 2 micron pillar and have it really dense on a surface in something that we can cast like silicone. And then I'm pretty sure it's going to work, and we'll actually have Gecko tape. Okay, see you next time. Bye.